Do we start already?
Yeah, sure. So go ahead, talk number 3.
Okay. Thank you. Yesterday we looked at some universe where every group is nilpotent. And we look at the Malus conjecture for nilpotent extensions, and on the other side of the world where people study class groups, we see that this crucial property of nilpotent groups, which is the Frattini argument, in some sense forces the existence of this genus field. Therefore, when you look at class group part, for example, you look at the P group extension and the P torsion of the class group, there's something pretty special. In the smallest such group like the quadratic extension, we look at the 2 torsion, the 4 torsion, and there are many interesting stories following from Alex's work. And I believe some in the afternoon we will hear from the talk on the 2 part of this class group. And at the end, I said, okay, if we look at the other part, the other P for quadratic field, things are completely different. So today we are going to look at the other part of the class group. I also said at the end that there are this randomness coming up for 4 part of the class group of quadratic field and 8 and so on, where Alex describes those randomness from his Castle-Tate pairing, and the way he understands these randomness is from the Markov chain. And this version of understanding the probability is not currently how we understand the other part. So that's what we will talk about today. So set up. We fix a Galois group gamma, and I have been using L yesterday. but since I will write a lot of P, so I will use P for the part of the class group we are interested in, and I will assume P does not divide the size of the Galois group throughout the whole talk of today. So how do we understand the class group where K has the Galois group isomorphic to gamma? Okay. The first step is the reduction from yesterday's talk, which is by class field theory, if you start with some, let's, for simplicity, just quadratic extension and an unramified extension with size L, which is 6 unramified, then this Galois group is going to be dihedral. So this is going to be the admissible group for this class group question. And the class field theory gives us this bijection that if you look at a surjection from the class group to CL, then up to some automorphism group factor, you can relate it to this M in the field diagram. Sorry, I just said I'm going to use P. I should stick to that. Okay. And M over K are ramified. This, for each K, such object is mysterious, and we don't have good upper bound on this, as I mentioned yesterday. So the idea is to put them all together, and hopefully we get something better. And so this will correspond to the number of dp extension bounded by some x, where we put this L minus 1, where this x should be, if p equals 3, this is going to be 1, and for general p, I think it's going to be 1 L minus 1 over 2, the index of the dihedral group. So let's say for p equals 3, for sure that this is correct. Sorry. Okay, so here this prime means that this unramified condition is translated to something about the discriminant of this field that is corresponding to square free in the case when p equals 3. And in fact, you actually get something proved through these averages, and that is for quadratic field. Positive or minus means that imaginary or real. The average over all such quadratic field is 1 if it is imaginary, and if it is 1 over 3, and that is totally real. And this is for gamma C2, p equals 3. And this is the only case we know that is when the gamma group is C2. So it is basically done through proving Mahler's conjecture for S3. And you can use the sieve idea that I mentioned on the first day's talk to get the square free. Other example is when the gamma is S3 and p equals 2, and the corresponding Galois group, the admissible Galois group for the Mahler side is S4, and you will see that K is summing over all the cubic field. Take the average, and you get 1/2 if R1 equals 1, and 1 over 4 if R1 equals 3. Okay. This is, I said that we would like to avoid those bad primes, but since we have very limited examples, I think it's good to mention. And this is done by proving Malus conjecture for S4 with some condition on this discriminant. And a more recent example is just a slightly strengthened version of the original Davenport-Hellbrown, and that is when gamma is some Rees product, and again P equals 3, but basically this is done via understanding the Malus conjecture for S3 Rees product. And here this U just means here is if you have a Rees product, then you can always find a unique index 2 subfield in here. So K and F are completely described by the Rees product structure, and U is the rank of OK star minus the rank of OF star. So you're fixing that as your signature condition, and this is the statistic for the relative part of the 3-class group. Okay. So the question for us is, we have these kind of averages of class group. How does that tell us the distribution of the class group overall? And so the strategy is completely different. Our hope is to get enough amount of information, averages to understand the behavior of our class groups. So the key word here is what do you mean by enough amount, and what is the behavior? So we will talk about firstly what is the behavior, and then what is enough, and then maybe if we enough time, how to actually gather these averages. Okay, so this is our question. So before I start the first question, let's get a detour to the Malus conjecture for abelian extensions over general number field. Okay. Okay, so recall that on Tuesday, we look at this object to parameterize all the abelian extensions over Q. What this is saying is, if you don't care about more refined behavior of Abelian extensions and local conditions, that's a completely different story. If you only look at the ramification information for Abelian extension over Q, so everything is transparent. And now, if you want to generalize this whole idea to general number field, what is the naive approach? Okay, if you come from a different background, the naive will means different strategy for you. If you, okay, over Q, okay, remember we talked about this free product of all the inertial group. So the natural naive guess is maybe we just take the infinite product of all the OP star, because those things, as explained in the last talk, will tell you where is the inertial group for your Abelian extensions. And this has problems, apparently. The issue is that you cannot see all the information about the Abelian extensions over general number field. It's not large enough. Basically, because there are unramified extensions of your general number field, and if you map all the OP star to trivial, you should still be able to see some Abelian extension unramified, but this is not telling you that. Okay. Okay, so, well, there is a pretty, okay, so just as explained in the last talk, the fix is you pick a finite set of prime S, and you form a slightly larger infinite product with good topology. And then this time, hopefully, we get everything, because this image will tell you the Frobenius of your Abelian extensions. And if I ask all the Frobenius to be trivial, then that will kill the class group. So then we get a big enough universe. And then you will see another issue coming up. This is too large. There are too many. Not everything, not every map is legal. In the sense that, how do you know you are really efficient when you choose this S? Okay, you can possibly choose too large S, and then when you have, for example, P1 and P2 corresponding to the same ideal class, you cannot ask them to behave in a different behavior in your ramified extension. So you need to compensate this by the unit. Okay, so this is derivative of the unit theorem. To compensate that, this is the correct object to look at. And then this is some not so directly useful information for studying class group. But we can try to parameterize all the Abelian extensions via this way, and our unramified extensions will be corresponding to the class group. Correspond to unramified Abelian extension. And then they will be corresponding to, via this parameterization, which is kill all the ramification. is simply just a bunch of Z mapped. And you have this OK star as the S unit embedded into your universe. And the dirichlet unit theorem tells you that up to some torsion, this is isomorphic to Z, again, to the size of S, if for imaginary quadratic. The first example. And then, now, to understand the Hilbert class field, you just need to make your choices for mapping Z to S to make choices from the Z to the S to the Z to the S from some map by connecting this. Okay. So if focus on the P part of class group, this is exactly saying you have a map from ZP to the size of S, a linear map to ZP to the S, and the co-kernel of this map is exactly modeling the class group of your quadratic field. Okay, so how would we know about this map then? We know nothing, not too much about this. This is where the randomness come from. Okay, so the idea is that this embedding of the S unit into this copies of Z is random. Okay, so this map, if it is random, what does it say for the behavior of this class group? Now, we can compute as these theorem, for example, Davenport-Howell-Brown is working, which is to understand the expected number of surjections from your class group to an abelian group. Okay, so if I have ZP to the size of S, let's say, and is the size of S, this is my class group. To understand surjections to such abelian group, we can just choose suitable map from ZP to N to A, and then understand how many M are there to make this computation zero. So we are going to look at the most natural way to think of this M, which is the Haar measure of some n by n matrix. And so write it in on the way. Let's call this F. This is the number of F from with ZP to the N mapped to A, where once you fix your M, you want the image of M is contained in the kernel of F. And the easy trick is to switch the sum for each surjection from ZB to the N to A. You are, after you switch the sum, you're asking, oh, what is the measure of such matrices such that the image is contained in my fixed F? Okay? And this is not so hard. Once you fix F, that means you have a particular subgroup inside where the quotient is A. Then to map M inside this W, you just need to choose your M basis inside this W. And the probability for doing that for each basis is just the size of A to the N. Okay? And now you can just add up over all these F the number of surjections from ZP to the N to A and divide by size of A to the N. Well, we have encountered this problem before. You wanted to understand surjection, but it's just easier to do homomorphism always. So remember that we have this Mobius function that help you do this inclusion exclusion where this is a Mobius function. Okay, rewriting the surjection and divided by size A to the N. Well, the homomorphism is simply just the B to the N, size of B to the N. So you can see that this is going to be equals to something that is dominated by the first term, and all the other thing goes to 0 when N approaches to infinity. Okay? So that recovers the number you see in the first theorem. And we can, so the imaginary is really important because you use the structure from the Dirichlet theorem, Dirichlet unit theorem, and you can easily recover this calculation for the real quadratic field if you just use one more rank for your S unit, because you get one more infinite time above your quadratic field, and then you just add +1 at suitable places. Okay, I think I only have these +1, and then you are done. So, which is a completely identical argument. And then this give you the real quadratic field. Okay. And now, this only tells you what is the average, and our hope is to actually understand the probability for the class group to be a particular P group. So now if you do the other problem, it is also probably very doable. Okay. The probability for my coconut to be isomorphic to A is what? Okay. Look at all the possible W in that ZP to the N, where the quotient is isomorphic to A. And then you ask, what is the probability for this coconut to be actually equal to that? Okay, so for the image to be equal to this W. And this is something you can break down to two steps. The first step is that the image is containing W. And the second step is that it is exactly equal to W if you already know it is contained inside. Okay? And then, when you fix W, the probability for your image containing there is just the same calculation we have done here. It's the index of the quotient, which is 1 over A to the n. And then if you know you're already mapped into W, which is also isomorphic to Z to the n, the density that it is surjective is something you can write down just by looking at the FP quotient. So you just need to understand the number of such W, but this is closely related to the number of surjections again, because there is this bijection, only up to some automorphism group of your quotient. And then you copy what you have here. And now, as we have done this calculation, this is the A. As we have done that calculation with Mobius function, you can believe me that as n approaches to infinity, this is going to be just the size of automorphism, where A to the n is cancelled by the leading term here, and multiply this interesting number. Okay, so from this way of looking at this random matrix, you can pretty quickly understand what is the expected averages for surjections, which we called the moment against the A moment. And you can also understand what is the probability for the class group. And this is usually, this is how usually the Cohen-Lenstra is phrased, that for imaginary, real, quadratic field, the probability for the class group to be isomorphic to a particular P abelian group is inverse proportional to the automorphism group. And if you are looking at the real, then you also add an extra factor. So you can also modify this part when the rank is n plus 1. I think, okay, just to be careful here, you will starting from 2 to n plus 1, and sorry, it's still 1 to n plus 1. Wait. Okay, it's starting from 2. Okay, this is starting from 2 to n plus 1, and then we have n plus 1 here, and I equals 2 here, and I equals 2 here, and that's how this calculation is done for totally real. Okay, so this is very nice and tells us what is the expectation for quadratic field. And now I'm going to ask the harder question that for general gamma, what's the expectation for the class group? is that if you have a class group, then it always corresponds to dihedral group equivalently. That means there's only one action from gamma on the class group, which is -1. But if you look at general gamma group, then there will be extra structure coming from the gamma action. I should mention that the whole idea of using this from OS star to look at this Cohen-Lenstra heuristic is from Elmer Vantage. Okay, so before this board. This is contained in some early 2000 paper of Elmer Vantage. So now, if we look at more general gamma extensions, we still want to do the same thing. Recall that we have been looking at this from the setup of class field theory, and to simplify the whole situation, let's just make sure that S is some, if you pick some set of rational primes from Q, make sure your choice is always split inside. Okay. Choose V that. Q. So this is always possible. You can actually see that from class field theory. You can always represent ideal class by prime that split in your extension. Now, if you do that, then the class group is now modeled by these product above your chosen rational prime. Okay. Above S, proportional by OP star. So instead of just looking at them as some copies of Z, we will need to remember the gamma action on this set. So it's not so difficult to show. You will get the induced module from your decomposition group to your gamma group, where, yes, we have assumed this decomposition group to be all identity, which means you get just the ZP bracket gamma. And those are for the prime that is smaller than infinity. And there are also, I should always mention that there are S infinity always contained in there. And for S, for the infinity place, it's possible that you have different gamma group locally, which means that you can have different possible choice of complex conjugation. And this is either identity or C2. And this is going to be the source for our okay, so let me be sorry, this is not what I meant to say. Since we have assumed 2 to not divide the gamma group, when we look at the P part, the infinity part just does not show up, as this is a C2 quotient at most. Okay? So what this is appearing is when you look at the S unit contained in your diagonally embedded in there. And the Dirichlet unit theorem is also telling you the gamma action simultaneously. And if you don't care about particular copies of a trivial representation, then this is isomorphic too. Like this level, let's say pro after this is pro p, completion of everything from the top, and this is isomorphic too. Just a direct product of primes above p indexed by the prime above S. And again, it is going to be isomorphic to some direct product of the induced module just for these small, for this finite place, and then you have these. Now you see interesting contribution from your infinite data group. Okay, so we have a setup that we can start to look at the map, starting from the unit into your ZP gamma to the n. And this, we hope, to model the class group. Okay, so we need to be a little bit careful because we have included this trivial copy of ZP to simplify the calculation. Therefore, when we say the co-kernel of this M should model the class group, you throw away the invariant part of gamma. Okay. So this is more or less just up to some trivial part. As you also always do if you look at this two part of the class group. Okay. So now you can do the similar calculation. So for any A that is a gamma, the ZP gamma module, where since we are living in the side where P does not divide the gamma group, the invariant part is trivial. Then looking at the co-kernel of M to A, the expectation for the number of surjections is again number of F from this to a particular A surjection. Which respect the gamma action and satisfying the same condition. And then you switch the order of the summation, you get to ask, oh, the number or the density, the measure of those random matrix where the image is contained in the kernel. And since when you fix the F, you fix the W inside this, this big group, then you just need to make sure all the bases is mapped into that W. Since it is gamma invariant, you can freely choose what maps to for your ZP times 1. And that is with the density exactly 1 over A. So you get the similar term showing up. And then you need to decide what to do for this component. And this is, say, to choose where this go. We'll go to the other side. Gamma ZB. Where this is A, you want to map into this W. It is equivalent to the situation where you just look at the part of the within the regular representation for this side. Okay, so what is the quotient for this side? It is just coming from the Shapiro lemma that if you want to map the particular part of A that comes from this component of the representation, is you map this representation to A, and that is isomorphic to the home of ZP to A when you view this as a sub-representation. And now ZP is a trivial representation for your subgroup, so this is just the fixed part by your A. Okay, where C is the complex conjugation you choose at the beginning. Now we can finish this calculation. You just need to understand the number of F, that is the surjection. Okay, similar. And using this Mobius function, you still get those sub-modules containing A that as gamma module as at the same time. But nevertheless, no matter what you see, you will get all these smaller terms approach to 0. So this is going to be just A, C, okay, as n approaches. So, this is really nice. It tells us that when you look at the general gamma extension, where at infinity now more than totally real or totally imaginary, depending on different choice of the complex conjugation, you will, I shouldn't say complex conjugation, depending on a different choice for the local gamma group at infinity, you will get the exact distribution from this moment. Okay. We'll say more generally, you can see this calculation is very flexible, starting from any base field. So we have been assuming our base field is Q, but you can do everything over general number field, and then when the choice of dV at all the V above infinity is chosen, all the calculation is local if you just carry over this algorithm. And the expected number of surjection is going to be 1 over all the product and fixed by the local gamma at infinity. Okay. So this is what we call the moment for this distribution. And now, how do you come back to the probability? And as you can see, I'm not going to do the probability for this one. Instead, there's a nice black box where you can plug in for this sort of questions. For this particular setup, when you look at the Cohen-Lenstra distribution, this is done by Wei Tong and Wood, but in the more general setting, by the work of Selwyn and Wood, we know that these moments will uniquely and explicitly give the formula for probability, and for this case, if you go through this black box, you will get the probability isomorphic to a particular A is inverse proportional to the automorphism of A as a gamma module, and this factor you have seen in the last computation. So this factor is not so surprising. You can try to do the probability distribution calculation as we did it before, and you will quickly see it show up. But to actually finish the probability calculation, it will be requiring more work. So this is really nice because in some sense, even the Cohen-Lenstra paper is still difficult to parse when you have an explicit example that will require some amount of work. So the last part, I will talk about the issue that so when we assume this moment will transform nicely to the probability, what does the enough amount of information mean? Enough amount of information means that you just look at surjection from the class group to some gamma module, and look at its average, and calculate this moment. And then you should be able to work out the probability. But when we say k is smaller than x, in all known examples, this explicitly means the discriminant of k is bounded by x. But this is not always working. And the reason is that you will have many k that come from one intermediate subfield. In fact, this is not even one big families, but many big families containing a single intermediate field. have this number so that it is not correct. For example, in the theorem of this Rees product, C2 Rees H, instead of put relative class group on the top, if you put the whole class group on the top, that will be exactly the situation the first problem comes up. And this is firstly written down in the paper of Bartel and Lenstra. And to fix that, the proposal is we use not discriminant, but the product of ramified prime. Okay. I should mention that in the same paper, there's some other issue about Cohen-Martinet and Cohen-Lenstra. But since we have been just discussing the P part alone, it's not going to be a contributing problem for this equality. Okay. And the second thing is when we look at the summation over all k, you still have problem for these invariant. So, replacing discriminant with radical, you get rid of those big fibers containing intermediate field, but not cyclotomic field. And this is firstly noticed in the paper of Cohen-Pagano, and in the more recent paper, I give a more careful discussion on what is the reason from a group theoretic way. But all of these are kind of issues for this problem from the denominator. I.e., the way you order things is already wrong. But more interesting is when you look at the numerator. So that is, if you have extra roots of unity containing your field, the distribution will truly behave differently. Not in OK, but in the base field OK. But OK, so if there's something contained in capital K, then there's other issues, but this is even earlier than that. Okay, so I will stop here, and tomorrow we will discuss what is the reason contributing to this. Thank you.
Are there any questions? If not, then let's thank the speaker again.